Okay, are we on?
We are on.
Hello, audience. So this is a tutorial session in the ICDE 2020, tutorial 4 on modern large-scale data management systems after 40 years of consensus. This tutorial is in 2 parts. So we'll go from noon to 1:30 for part 1, break for 30 minutes, and go from 2 to 3:30 for part 2. We have a great set of presenters for this tutorial, and I'll briefly introduce them. Mohammed Amiri is a PhD student at the University of California at Santa Barbara. Divi Agarwal is a professor of computer science at the same university. He's a distinguished scientist, ACM distinguished scientist, ACM fellow, IEEE fellow, and AS fellow. Professor Amar Abadi is also a professor at the same university, California, Santa Barbara. He is also, he has won the co-recipient of the Test of Time Award in EDBT ICDT 2015. He is also fellow of IEEE, ACM, AAAS, and he has published over 400 articles. So knowing them, some of them personally, I can tell you that the collective research and development they have together is so vast and so cutting edge. They will give you a good thing for your attendance. Just before we start, I hand over to the speakers. I just want to go over a few protocols for virtual presentation. One is, audience, please mute your video and audio. Click your video settings in Zoom and deselect the spotlight my video when speaking option. And finally, choose to view in speaker view. So this seems to optimize or maximize your experience for a virtual presentation. Coming to the question answer part, since it's not possible to take it in a real time, question answers in a real time, you need to post your questions on QA and Slack. QA is preferred. I will be monitoring the QA chat box, and then when the speakers are ready to answer some questions, I will select a few of them and request them to answer. So we can all follow this. Now I'll hand over to Amar Abadi for the tutorial. Amar.
Thank you, Sharma. Thank you to ICDE for inviting us and hosting us all remotely. This has been a very good experience, both especially from an educational point of view. I mean, we are adapting to this large-scale distributed system, and we are all globally distributed around the world, and we are participating in a virtual conference together. The foundations of a lot of this work, this global distribution of interaction, management of data, etc., is really founded in some very important distributed systems results, distributed computing protocols, consensus protocols that have been developed over the last at least 40 years. We are picking our landmark date as to start time from 40 years ago, when a landmark paper was presented by Lamport, and that paper was is reaching agreement in the presence of faults, and this is when Lamport, Pease, and Shostak proposed the Byzantine agreement or consensus protocol. This paper appeared exactly to the month, actually 40 years ago. So in April 1980, it was published in the JACM. Let me go back. So what we're going to do today is we're going to basically develop the foundations of consensus, agreement, and show the various protocols that have evolved over the last 40 years, as well as try to tie it to what is happening in the modern world. What's interesting is that a lot of these foundational protocols, Byzantine agreement, was proposed, as I just alluded to, 40 years ago, and it remained for a long time through the early 2000s as an academic, more or less, exercise. There were lots of papers, lots of interest, but if you think of it from a database world, we were not really affected by it. We worked in an environment that was a lot more benign, less distributed, and actually the challenges of distribution from a practical point of view hampered the progress. However, in the early 2000s, with the rise of the cloud in the context of these large companies like Amazon, Google, Facebook, etc., the need for large-scale distribution became critical. And we couldn't evolve, we couldn't develop what we wanted. We couldn't manage our data in a fault-tolerant manner without relying on these protocols. So we see this rise in interest and very practical interest in the results of the previous 20 or 30 years, starting with like around 2000, around that time. Fast forward again another decade, and we have the rise of blockchain, Bitcoin, Ethereum, Algorand, etc., all of these. And again, they have to go back and pick up protocols and ideas that were developed in a previous context, also typically in a much more academic setting, and trying to use them and actually succeeding in using them in a practical setting. The first wave at a very high level focused on developing protocols that are fault tolerant, but from a crash point of view, fail stop, so a processor fails by stopping. The second wave, which is what we are living in now, and we will come to this at the very end of the presentation, is within the blockchain untrusted infrastructure, and this brings in malicious failures to discuss. So what we're going to do more or less in this presentation is we'll motivate why we're doing what we're doing and why is the interest in these consensus protocols. Then we'll go through some of the basic protocols, and I will start with presenting to you Paxos in a fair amount of detail so that anybody who is not familiar with it should be able to get a strong grip on how Paxos was developed. Then we'll go through a series of optimizations, exploring the space that we are working within. So different dimensions of the problem, kinds of faults, number of faults, etc. And then we will switch to foundational work on malicious work, and that goes back to Castro and Barbara Liskov's work, and then move on to newer applications in the context of blockchain and the cloud, etc. So so I'm going to start. The plan is, this is a tutorial by Mohammed, Divi Agrawal, and myself. The plan is for me to start, and then I'll hand it over to Mohammed, who will continue. We'll have a break, and then Mohammed will start after the break, and then I will take over at the end. So as I alluded to, we are really celebrating 40 years of Byzantine agreement, the famous problem proposed by Pease, Shostak, and Lamport in April 1980. So we are now April 2020. So this is really a very important problem. So let me motivate why is the need for fault tolerance and what is happening here. If I have one computer and the computer fails, I don't have the data. So this is not good. I'm not able to do what I'm doing. The focus obviously in this tutorial is on data management. A lot of what I'm talking about can be parallel. There is an analogy for it if I'm talking about processing and you go in the route of MapReduce and Hadoop. We are not going to talk about that. We will be focusing on consensus, and the focus is for what's called state machine replication. So to get around the problems of failures, what we do is we replicate the same data object and have multiple copies of it, And if an update, the main challenge is what happens when updates takes place. When you have a data object, you have two types of operations, irrespective of whether you're using high-level language like SQL or any other language. At the bottom level, we have to deal with two types of operations, reads and writes. So when a write occurs, when there's a change in the state of the underlying system, we need to run a consensus protocol to make sure that all the copies are up to date. In database language in the 80s and 90s, we used to call this replica control, so replica management or consensus among all these different servers. Why is this good? Because if a failure happens, then a client can still access the data and find it. So that's in a nutshell the problem of state replication. State machine replication. What I'd like to do is I'd like to do this in a fault-tolerant manner. So I want to execute this consensus protocol in an environment where failures can happen while you are executing, not like in this naive picture where the failure happens, say, after the consensus. So the consensus problem is basically you have a set of nodes, and the set of nodes need to reach agreement on a particular value. From a database point of view, we often think about it as like a commitment protocol. There are analogies, and I'll tweak into it later on in the talk, where basically you have some information, some updates that have taken place on multiple sites. They are consistent. And what we would like to do is we would like to all of them to agree on committing that value. That's very similar to the consensus at some level. So, as I alluded to at the beginning, this problem was studied, especially in the distributed computing community, in the theoretical distributed computing community. So if you want, you can look at the principles of distributed computing, which is the POTC with a C, the conference, and they had lots of papers. Then we had, and there were lots of papers in the 80s, 90s, triggered by that seminal paper that I introduced of Pease, Shostak, and Lamport. Then we have Google starting in the late 90s, and they need to build a big distributed system that manages data, the data that is about all the websites that are around for all practical purposes of the world. Obviously, they do not want to maintain strong consistency. They want to maintain fault tolerance, but they don't need to really have strong consistency between the different copies. So there's an interesting idea which comes up, which is to separate the data that you are going to access, and that might have relaxed eventual consistency type of criteria. On the other hand, you have metadata, which manages the distributed system. It knows the data is, what is happening, where the different pieces of data are and where they are stored, lock management, etc. This needs a very reliable, consistent system. Reliable meaning it has to tolerate faults. So at that time, they developed this very interesting subsystem called Chubby. So the entire system is below here, and it has replicas, it has all the good stuff, but it doesn't need to be consistent in a highly consistent manner. However, the metadata, the information about the running of the system, needs to be very up to date and consistent and highly fault tolerant. And they developed Chubby, and to develop Chubby, they needed a consistency protocol, a consensus protocol, and Paxos was used. As far as I know, this is the first instance where Paxos was used in an industrial setting. A few years later, actually, Google again built an infrastructure for managing replication, and that is the Google Spanner system. And we will delve into it a little bit more later on, but it requires replication at a geographical scale, what often is referred to as geo-replication. So every data center is replicated on multiple sites, on different locations. So on the East Coast, on the West Coast, in India, in China, etc. they needed to develop this. They needed a Paxos algorithm to maintain the different replicas. And again, this is one of the earliest times where Paxos is used at a large scale distribution. So in Chubby, it was still within a data center context. Here with Spanner, it actually spans multiple data centers. I'm just picking these two examples. There are a lot, this triggered a lot of interest in the community, especially in the industrial setting, where a lot of systems were developed that used consensus protocols. For example, Amazon developed Dynamo early on, and again, it needed a Paxos or a Paxos-like inspired type of algorithm. We know that Cassandra was inspired by Dynamo, and Cassandra eventually evolves into protocols that are used or infrastructures that are used in Facebook, etc. So you have a large scale interest in developing these protocols. Fast forward to the teens, where we are saying now, where we are living now. So in the 2014, 2015, up to 2020, we have a rise of interest in blockchain. And again, there are different kinds of blockchains. I'll get more into it at the very end of the talk, but basically we have permissionless blockchains, which are used for cryptocurrencies, and permissioned blockchains, which are used in the context of much more of a database context, like supply chain applications, etc. Again, these blockchain systems rely critically on replication. Replication among untrusted components. If you go back to the last two slides, both Spanner, Dynamo, etc., Bigtable, all of them worked in an environment where the assumption was processes would fail by crashing, just fail stop. Once we get into the blockchain world, we are interested in malicious failures, because you are storing the data on untrusted components. You are storing the data, the blockchain, the replicas of the blockchain, which is basically a linked list, on multiple sites, and you don't know who they are. So they are untrusted. So we needed a consensus protocol in this context, and what is used is often some of these protocols, not some of these protocols. And so Hyperledger Fabric is an example of a blockchain system that uses consensus. Bitcoin is an example of a system. Basically, it's permissionless, unlike the previous slide, which was permissioned. And they, again, need to solve the consensus problem. And here they are going to use a very radical, different approach. I'm going to say this tongue-in-cheek a little bit, using proof-of-work approach to achieve consensus again. Who has the right to update the items and how to do it in a consistent manner? So the theme of having multiple copies and updating them consistently has a long thread that goes through a lot of these industrial systems. So to understand it, we need to develop the foundations, and the foundations are basically going to be based on what is happening when I have multiple replicas of data. So here is a picture that will illustrate to you how we are thinking. And this is actually taken from some slides from John Oosterhout when he was presenting Raft. So we have clients and we have servers, and we have multiple servers. They are all going to be copies of each other. And what we would like to do is we would like to have a log, and this is typical in distributed systems. You have a database or a server that has a state, and the state reflects a sequence of operations that were executed on that object. So think you have a state and it is triggered by operations. If I have multiple copies, so I have 3 copies, for example, here, if all of them execute the operations in the same order, then the current state of each of the 3 different replicas will be identical. So the problem of managing replicated objects can be filtered down to a problem of managing a replicated log, where the log becomes consistent across the different copies. And if I'm able to update the log so that the order of the operations is identical among all of them, then I know that eventually the state of each of the different replicas is going to be the same. So if we have a client issues a new command, it needs to be replicated among all the different logs so that they are executed on the state machine to be reflected in the state of the object or the application. So if a new command comes, we end up needing to execute a consensus protocol, and that will be the heart of what we're going to be discussing. Once that consensus protocol has been executed and all the copies have received the new operation, let's call it the shell, then I'm going to incorporate it into my log. This is everybody gets the same operations. We assume they are all deterministic operations. They are all going to be inserted in the right order. Once they are inserted in the right order, they can be executed on your state machine. And once you've executed it on the state machine, you have the answer, whether it's an update of a file or an update of a replicated database, SQL tables, whatever. And then you tell the clients, hey, we are done. So this is basically the operation that happen in a state machine replication. We have an operation, you have a consensus protocol, you update a log, the log is totally ordered, and the head of the log is what is executed, and you move on. So what do we want? Well, we would like to have, typically when we talk about correctness, we need safety and liveness. So with safety means basically bad things do never happen. So only a single value that has a value that has actually been proposed by a client is actually executed. Only a single value, if there are competing clients that are issuing commands, only one is chosen at any one given time to put it at the head of the log. And a node never learns a value that has been chosen unless it actually has been chosen. So you don't know things that are not true. But then we also, usually we like to have a liveness property. Good things eventually happen. I mean, I could always do safety, bad things never happen by doing nothing. If I do nothing at all, nothing is going to happen, but nothing bad is going to happen, but also nothing good is going to happen. So liveness is that eventually good things happen. Some proposed value. So if there are competing values that are being proposed, I would like one of them to be eventually picked. And if a value is picked, a node can eventually learn of its value. So we are typically interested in safety, but also eventually good stuff happens, liveness happens. There are multiple modes in which we can explore the different protocols we are going to talk about. And these different dimensions have been studied ad nauseum in all the different ways. Basically, we have a synchrony assumption, a failure model, a processing strategy, the participant types, and finally complexity. So let me take each of these one by one. So the synchrony is all distributed systems are typically divided into two types, synchronous systems versus asynchronous systems, and a third one in the middle. So the synchronous systems, you assume that there are known bounds on message delivery, processing power, all of these things, so that you can run protocols in rounds. So you know, if I'm off from everybody else by at most 50 milliseconds, and I can, as a result, adjust what is happening. A more realistic assumption is to say that the system is asynchronous. I do not know how long it takes for my message to get to you. The clocks of the different processes are not synchronized. So this is a much more interesting, practical setting that we would like to aspire for. Synchronous requires a lot more mechanisms to guarantee it. So tightly synchronous systems might be achievable, but asynchrony on large scale, especially a global scale. What is often explored is also what's called partially synchronous systems, which assumes that among the nodes there is a subset that can communicate in a timely manner, and then this might be reasonable in some context and might not be reasonable in an uncontrollable environment. So only an arbitrary number of nodes perceive an arbitrary slowness. We'll explore different protocols along these three different aspects. Then there is the failure model I've already alluded to. We can either have crash failures or we can have Byzantine failures. Byzantine is typically used to refer to malicious failures, and that's because the original paper of Lamport discussed Byzantine agreement and presented the agreement among malicious processes, and hence we often use the word Byzantine failure in that context. So in the Byzantine context, a node can do arbitrary stuff, anything it wants to do. It is not tied to a particular thing. In a crash, the node executes the protocol honestly, it follows the code, and then suddenly it stops working. There's no collusion, there's no lying, etc. Obviously, Byzantine is much harder to work on than a crash. And there are protocols, like I said, with synchrony and asynchrony that use the hybrid model. Some nodes might be crash and some nodes might be malicious. Then we have, from a processing point of view, from an algorithm development point of view, and this for a database audience, this should be obvious. We have pessimistic approaches, which guarantee that all the replicas are identical to each other and robust and everything is happening. You have to ensure you get your locks first before you end up executing things. So it's a pessimistic approach versus an optimistic approach where you allow the processes, the replicas to execute you, and then you figure out if there were conflicts, and then you might have to backtrack or do recovery. So this is, again, an aspect that we've talked about, that for database people is very common. A fourth aspect, which is very interesting and we were not as a community aware of it until very recently, is participant awareness, or the type of participation that is happening. Most of the work that was done up till the mid-2000s, 2005, 2008, you know the number of protocols in the system, you know who they are, you know a maximum number of failures in the system F. And this seemed reasonable. So all the protocols we'll be developing for the first 2 hours of the presentation are going to make that assumption. However, recently, with the rise of blockchain and Bitcoin and all these cryptocurrencies, there's been interest in environments where you actually don't know the number of participants. As a result, all the protocols that we were working on before cannot really work because they were assuming knowledge of the number of participants. Then there are the obvious complexity metrics. We are interested in knowing for a given protocol whether it had the number of nodes that it needs, the number of communication phases that it needs, and the message complexity. Okay, so this kind of lays the rubric of the 5 different aspects or dimensions that we will be analyzing our protocols within. And for each of the protocols we will develop, we'll give you a little table that indicates where they fit in with respect to these different aspects. So very early so Lamport's paper was proposed in 1980. We have Fisher, Lynch, and Patterson give us an impossibility result, which is the impossibility of consensus with one faulty processor. And this paper appeared in, again, this is a good year. We are celebrating lots of anniversaries. 35 years ago, exactly in April, it appeared in the JACM. Actually, I dug up the earlier version of this paper, and it first appeared as a conference paper in PODS, Principles of Database Systems. So although this is a very theoretical impossibility result for distributed computing, it's interesting to note that it appeared in a database conference to start with. So from the very beginning, interest in distributed problems, and especially distributed consensus, was critical in database applications. And we, as a community, were always interested in the most recent results because they were relevant for what we are doing, because we deal with data and we are interested in replication. So basically what the protocol is known by the initials of the three authors, Fisher, Nancy Lynch, and Mike Patterson. So the impossibility is actually a very negative result, because it tells me that even if I have the most benign type of failure, crash, and even if I'm guaranteed by the infrastructure that at most one process is going to fail, at most one, and even if the network is reliable, if I'm in an asynchronous system, and this is critical actually, the asynchrony here is very important. Since this is an asynchronous system, the impossibility result tells me that consensus is impossible. Consensus is basically that all the non-faulty processes agree on a value, 0 or 1, nothing could be simpler. One can look at this in the following way. If I desire 3 different properties, I desire fault tolerance, I desire safety, and I desire liveness. All 3 of them together are impossible. In fact, the FLP result, what it tells us is that to solve the consensus protocol in a crash environment and to tolerate one failure, you have to give up liveness, basically. So there is no guarantee of termination. So the impossibility is that termination is impossible to guarantee. Liveness is impossible to guarantee in an asynchronous system, even with crash failures. This is a very kind of disturbing and negative result. So as a result, there's been a lot of work trying to circumvent this problem. So one idea is to say, let's try randomization. So there's been a plethora of randomized Byzantine protocols. Instead of assuming asynchronous systems, assume a synchronous system, which is very reasonable. The problem here is that a lot of these protocols end up being expensive, both in terms of number of phases as well as in terms of message passing. They really are expensive protocols. And when I say number of phases, it is important because it's a reflection of the latency. Remember my first picture of the finite state machine replication. The client has to wait until consensus has taken place. If consensus takes multiple rounds of communication, it's going to take us a long time. So latency is hurt. Some people have proposed a failure oracle, adding a trusted component that could help us change the problem domain, make it a range of values or a set of values, etc. So there have been an exploration of different approaches. And there are lots of lower bounds that have posed. I'm not going to go through all of these. There's a lot more. This just gives you a snapshot of what there are lots of bounds that we are hitting on. And there are lots of problems that are variations on the consensus protocol, whether it's atomic broadcast, and that is again used, for example, in some of the systems like Dynamo uses some kind of atomic broadcast. There are various large-scale cloud computing systems that use that. Obviously, state machine replication I've talked about. There's group membership, who's a member of the system, and there is atomic commitment, which is dear to our hearts in the database world. So there are all connections. I'm going to actually have a few slides on the connection between atomic commitment and consensus later on. So let me get to our first protocol, and I will spend some time on it. So I want you to focus with me. And if any of you went to this morning's talk by Joey Hellerstein, he actually was saying that Paxos is one of the protocols that when I, as a teacher, stand in front of the class, I have to worry the night before. It's so full of subtle issues that we have to worry about it. So Here is the rubric that we've talked about earlier on, and I just want to make sure that, so all the different dimensions. So here, this is an asynchronous protocol, and this is the protocol, remember, that was developed by Lamport, I mean, in 2000, and actually in the late 1998, 99, and eventually it came out as Paxos Made Simple because he explained it in very complicated terms. If you're interested, that's an interesting blog of Lamport you can read. But critically, it is for an asynchronous system. So it's a very realistic system. It was implemented first in Chubby. So there's a lot of interest here. It's for a crash environment. It's a pessimistic approach. We know the number of processes, and basically you have, if you want to tolerate F failures, F crash failures, you need 2F+1. So to tolerate one failure, you need 3 copies of the data item. If you want to tolerate 2 copies, you have 5. That is reasonable, and the complexity is linear. So since this is an asynchronous system, Paxos will guarantee safety, obviously, but it cannot guarantee liveness. Liveness consensus is achieved if a large enough subnetwork is non-40 for a long enough an amount of time. So from a practical point of view, often this doesn't happen. So often this happens. So as a result, consensus is reached most of the time. But one has to remember it doesn't violate the FLP result. It might not terminate. So how does the protocol at an abstract level work? This is our finite state machine replication approach. The clients send requests to a leader. So it is leader based. There is one process that is chosen to be the leader. We'll get into this later. The leader needs to pick between these 2 different approaches and get consensus by sending messages to everybody, getting answers back, and then committing on some value and informing the client that it's been done. So it's a leader based. The leader needs to be elected, and the leader is elected by a quorum of servers, a set of servers. So if an update comes, think of this as the leader. The leader is going to send a request to everybody. We have n processes, tells it, hey, I want to be the leader because I have a value that I intend to push forward. He doesn't have to tell them the value now, but if he gets back from a quorum of sites, and in Paxos, it's a majority. Why? Because we need to have intersection. So 2 quorums must intersect. There must be an intersection between the quorums. And so an intersection is easily achieved if I have a majority, half plus 1 of the number of processes. That's why n needs to be known. We need to know n so that when I get a quorum, I know that I have gotten a majority of the number of sites in the system. Once I know I'm elected, then I make the value that I want fault tolerant. I distribute it. Once I know that a majority have stored that value, the leader can now know that it is reliably replicated and can be done and announce the decision. This is just a schematic of how it works. So we'll call the leader, because there might be more than one leader, more than one processor who wants to be the leader, we're going to call him the proposer. So the proposer starts, sends a message. The other ones are going to be called acceptors. So there's one proposer. There could be more than one proposer competing with all the acceptors in the system. This is the original terminology of Lamport. And then finally, everybody listens to the answer. All decisions are asynchronous. So there is no bounds. I can wait and I don't know when it's going to happen. So the critical condition on quorums is that at least there must be at least an intersection between any 2 quorums. This way, a new leader will know of a value chosen by an old leader through the overlapping acceptor. There has to be an overlapping acceptor. So if I have a majority, here is an example of 7, then any quorum of size 4 will have a non-empty intersection. Paxos is leader-based. Every time there's a new value, there's going to be a ballot, and this ballot is the one that we are going to use. So we're trying to get consensus on a single value. We're not worrying for now about the log, the entire log. I'm just trying to get consensus on putting a value at the head of the log. So for every new value, you need to have a ballot number, and the ballot number is unique. It's basically a number that is incremented plus your local process ID to break ties. So as a result, you can come up with a total order on all the different ballots. Paxos has two phases, as I alluded to. First, you have a prepare phase to get yourself elected as a leader, and then you try to get the processes to accept your value. A critical problem is what happens if the leader fails. If the leader doesn't fail, it's really a simple problem. The problem is if the leader fails. So let's look at this example to motivate what arises, some of the complexities. I'll just try and tweak into some of the complexities of the protocol. So there is a protocol, there's a value, and it goes to a process, process one. Process one gets this value from the client, wants to be the leader. It creates a new version, a new ballot number, and announces it to everybody. A majority agree, so itself plus two more. So we have 5 sites here, so 3 is a majority. So I know I am the leader now. I got an agreement from majority. I'm now going to take that value that I had, and I'm going to propose it to all of these guys, and I'm going to try and get a majority again. Majority, because if a majority survives failures, then I can continue making progress. So I will get to a majority, and now I'm happy. I got a majority to agree on my value. Now the problem in a distributed system is everything by message passing. So process 2, process 3 do not know that each other have already sent a message. So we need to have a way in which the leader needs to inform them. So the leader should announce the decision. But what if the leader fails at this point? Then we have a problem. So the value V was chosen. There was a majority that agreed on it. And any new leader, because our leader that we were discussing has failed. So any new leader must recover that value. So we need variables that are persistently stored in each of these accepting majority guys, processes, persistently meaning on their disk, to indicate the value that was accepted. So we have 2 important variables in the protocol, accept val and accept num. So now let me give you the protocol, and I will hopefully finish in 5 minutes. I'm running over my allotted 45-minute slot. So we have a ballot number. We have an accept num, which refers to the ballot number that was last accepted by a given process. So it's initially 00, and an accept val, which is initialized to bottom and is going to incorporate the accepted values that are eventually going to be accepted. These slides are inspired from work by from slides from Edith Kaider. So this is the prepare phase. The leader wants to got some value from a client. It's going to increment its ballot number and sends out to everybody, hey, I want to be the leader. This is the prepare phase, and this is the ballot number. Notice the leader does not send the value. It's for the second phase. All he's trying to do, because there might be another leader there might be another proposer who's trying to be the leader. So the goal is to ask them to join my ballot. And remember, they could be competing processes trying to go in to become leaders. So let's look at the view from an acceptor, from a cohort point of view. They receive this prepare with a ballot number. So this is the message that was sent. And now we have the receive. So it's a prepare and a ballot number. What they do is they compare the ballot that is being proposed, that just arrived, with their current ballot number, whatever their variable was. Remember, we had a variable here. This is the latest ballot number that this process ever participated in. So it's going to compare it, and if this is higher than anything else I've heard about, this is better than anything, I should join it. So I abandon any ballots that are older in time or in numbering, basically. And I immediately set my ballot number to this proposed val. So you take this ballot val, which I just heard about, and update it. What does this mean? It means that if I get any other proposals that have smaller ballot numbers than val, I'm going to refuse them because the condition is the same here. So I will only move up. It's a monotonic property. Again, this is reminiscent of Joey's talk this morning. There's a lot of monotonicity taking place. So if I do this, then I send back to the leader saying, yes, I accepted. And by the way, in case I had participated in a previous round, remember the example where we had the failure of the leader. We had replicated the value on a majority. So I'd like those not to die because they were accepted. They had reached a majority. So if there is anything, we're going to give them my accept num and accept val. These will be updated in phase 2. So there's a forward reference here that you need to just keep in mind. So the leader now, let's switch back to the leader. The leader waits to hear back from a majority. If it hears back from a majority, and if all the values are, this is a null. If all of them were bottom or null, then I just adopt my value. Nobody was competing with me, which should be the normal case. However, if some of the other processes send accept val, which had a value, then I take the one with the highest ballot number. And now I know that it has been replicated on a majority. I plan to accept this. This is actually a point of no return. I know that this value is committed, more or less. The leader knows this. And it sends accept with the value to everybody now. And so upon receiving the accept from the leader, they just accept it. If this is greater than their current ballot number, which is normally the case, you accept it and you send back to the leader, I'm done. And upon receiving an acceptance from the leader is going to decide on the value and we're done with the protocol. So it's a two-phase protocol. You have a leader election and then a replication of all the values. Paxos guarantees safety. I'm not going to argue to give you the proof of it, but it can suffer from liveness because a proposer could propose, like in this example, 3.1. Another competing proposer might propose 3.5. And so when the accept phase of the 3.1 comes back, it's going to be rejected because processor 3 had already seen something higher. So it's going to reject this. And then this guy is going to backtrack and is going to try and push for his own value again, 4.1. But then we get the accept phase of the first of the green protocol here again, and you can have this forever. So you could get into a situation where you have a live lock and hence liveness might not be guaranteed. Obviously, there are standard solutions. We do this whenever we have a deadlock situation or when we have a locking situation. You basically randomize the delay before restarting so that hopefully the chance of this happening is not too high. So in summary, we have basically a leader election phase and then a replication phase and finally a decision. So the question arises is why is this phase needed? Why is this initial phase needed? Well, it's needed because I need to elect a leader. So no consensus values are sent. It's only just proposing a leader in the second phase that the initial value or the latest value is learned. So what we can do is we can have a leader election phase by itself. And then once I am leader, we will try and have all the clients communicate with the leader, and the leader is the one who's going to do the execution of only the second phase. And so as an optimization, we only run phase 1 for leader election. Sometimes this is referred to as view change or recovery mode after a failure. And phase 2 is what's happening all the time. So it's very cheap. It's really just, once I'm elected as leader, all I need to do is to replicate, get back a majority, and then I know it's already been committed. So that's good. It's a fast protocol. So we have a leader election, and now updates don't have to go from the very beginning, but go to the acknowledged leader. If it goes to a client, to a process who is not the leader, that process might send it to the leader. Obviously, if the leader has failed, then you need to go back and run the leader election protocol. So this is what is commonly known as fast Paxos. So fast Paxos is a variation. It's a much more practical variation of Paxos, which basically has a particular site that is the server who's been elected as a leader, and he just uses the second phase of the protocol to replicate information. So this brings us to the end of Paxos, and I hope you have, it is much more subtle, and the best way to understand it is to try and implement it. And what I do in my classes is I have my students actually implement it. And it's the subtleties between the different phases and messages between the different phases is important. Paxos is notoriously complicated in its implementation. It sounds simple when I describe it to you, but it is not trivial. So John Oosterhout proposed with his student proposed Raft, which is equivalent to Paxos in terms of fault tolerance. So all the parameters at the very bottom are almost the same, but integrates the consensus part with the management of the log. And it is much, in some way it is much more understandable. This is debatable, but actually at Stanford they have done user studies and shown that people find Raft easier to use. And some systems have now been using Raft instead of using Paxos. So for example, CockroachDB uses Raft, Quorum uses Raft. There are lots of Hyperledger Fabric, some versions of it use Raft. So Raft can be used to replace it. It integrates the log management in a much more easier way to understand. Mohammed, okay, so let me try and go through these slides very quickly. I'm taking much more time than I expected. So I can basically, shall I continue, Mohammed?
Yeah, don't worry. Yeah.
Okay, I'll do that. I'll take 3 or 4 more minutes. So I've abstracted Paxos as leader election. So I get elected as the leader, then I make it fault tolerant. I get a majority of the copies to accept my value. And then once that is done, I asynchronously can announce the result. We as database people are very familiar with commitment protocols. So two-phase commit is very famous. What do we know about it? How does it work? Well, it's very simple. You have a coordinator and there are multiple entities. In this case, we have 2 people who want to get married. You ask them, have you committed the transaction? Are you ready to move forward or not? And if they all answer yes, then we commit the transaction. If any of them says no, then we abort. And if all of them say yes, then the coordinator needs to tell everybody, yes, you are committed. So in a way, we can abstract it as saying there's a value discovery. I do not know what the different participants want. So I need to get their vote. I need to know whether they are willing to commit or abort. So there's what we'll call value discovery. Then you make it fault tolerant. And in two-phase commit, how we do it, how do we ensure fault tolerance? By basically putting it on disk. I make it persistent. I make the decision persistent. I, meaning the coordinator, makes the decision persistent by putting it on disk. And then I announce the result. Now, this protocol is blocking, and that's why there's a lot of criticism about it. If there are failures, some sites might not be able to make progress. In particular, actually, if the coordinator and one site fails, the rest of the system can be held up. It's not even like they cannot abort, they just are blocked. So a protocol proposed by Dale Skeen and Mike Stonebreaker is three-phase commit. And with three-phase commit, you actually have an additional phase where after the value discovery, you make sure that a majority of sites know the value. Once that is done, you announce the result. Unfortunately, once you have that, you have to tolerate failures. So what do? Is we have a termination protocol for three-phase commit where a leader is elected and the leader needs to discover the value that might have been committed or not committed. So the decision needs to be figured out. So we'll call this a leader election and a value discovery at the same time. And finally, you do fault tolerance and then decision. So obviously, we have common things between Paxos consensus and commitment, two-phase, three-phase commit. They're both leader-based. They both need discovery at different times. They both need agreement, and they both have a decision. So what we did in 2019, VLDB last year, we proposed a framework, the consensus and commitment framework, which actually takes all of these different phases and shows how the different protocols are instances of them. So it's actually a very nice pedagogical tool to understand existing protocols. Three-phase commit has a leader election, which is only done if there was a failure. And then there's definitely a value discovery, fault tolerance, and decision. While Paxos has a leader election, has a value discovery if there was a failure, and then we have fault tolerance and decision making. This framework not only explains things, but also helps us to provide insights into novel protocols that we have developed in novel settings that are variations on this. I will not have time to do this, but I think I'll hand over to Mohammed. I think we should, are there any questions, Sharma?
Yeah, okay. So there is only one question.
Okay, good, because we are running out of time.
You might have answered it already. And the question is from an anonymous attendee, why not use 2PC instead of using Paxos? So.
Oh, okay. So I think I explained it in the last unification framework. So there are these subtle variations between the two, and eventually they actually are instances of the same big idea. It depends on what we are assuming and where we are doing. So I think I'm going to hand over to Mohammed now.
Yeah, before Pablo starts, let me remind the audience to send in questions through the QA chat or the Slack channel. Both of them are open and I'm monitoring it. So if you have questions, please let us know. Thank you.
Okay, thank you. So I'll close my window and Mohammed can now share.
Okay, I'll try it. Okay. So is it good?
Yes.
So hi everybody, I'm Mohammed and I'm going to continue our thread on Paxos. I'm going to introduce some of its variants and then we'll continue on malicious failure and talk about different protocols in that domain. So I'm talking about Paxos, and as we saw, Paxos had 3 phases of communication. And we can use multi-Paxos, as Am said. We can have a stable leader and then reduce basically the phase of leader election. So we don't need to elect a leader for every command. However, what if we want to have a faster version? Fast Paxos does this. It says we can reduce message delay. We can reduce one more phase of communication by sacrificing the quorum size. So it's basically, there is a trade-off between quorum size and the message delay. So as you can see here, it increases the number of nodes from 2f+1 to 3f+1. However, it reduces one phase of communication. So it's still asynchronous, it's still crash fault tolerant, and it still knows the number of nodes. And why it is 1 or 3 phases? Because it uses an optimistic approach. At the beginning, it tried to have a fast round using an optimistic approach. And if there is some failure, then we need to kind of recover from that. And that's why we have basically 2 variants, 1 phase or 3 phase. So it basically generalized the Paxos. And the intuition behind fast Paxos is if the leader has no value to propose, a client can instead propose values by sending accept message to all nodes. So in Paxos, we have the clients who send accept message, who send their request to the leader, and then leader is going to send accept message to other nodes. However, in fast Paxos, the clients directly send accept message to every node. And then backup respond as in basic Paxos. They send accepted message to the leader. So how does it work? If the leader has no value to to propose, it sends a message called any message to all replicas, and basically enables them to select their own value, the values that are coming from the leader, that are coming from the clients. So it is not basically a phase of the fast run. Fast run starts from here. The clients send accept message to all replicas, and then the replicas send accepted message to the leader. And if only one value is accepted by all replicas, then it is done. The leader can send a commit message to everyone and sends a reply to the client. So as you can see, we reduce one phase of communication between leader and all replicas. However, what is the problem? The problem is we might have different clients who try to propose values at the same time. So we still have this any message, and then we have clients who send accept message to the different replicas. We have two different clients, and then replicas, as you can see, we have two different colors. These two replicas accept the first request, the last replica accept another request, and here the leader says that we have different values. So we need to move back to the basic Paxos. We need to send another accept message and another round of accepted. So if there is a collision, then we need to resolve it by going back to the classic round and sending accept and accepted message. So this is how fast Paxos works. And fast Paxos needs 3f+1 instead of 2f+1. Why? Because the intersection of these fast round and classic round is not only a single node. We need to have majority of these fast round in the classic round. So the intersection of these two quorums is basically f+1, and that's why we need 3f+1 in fast Paxos. Another variant of Paxos is flexible Paxos. If you remember in Paxos, and we said, okay, any two quorum need to intersect on a single node. And these quorums might be leader election quorum or replication quorum. So flexible Paxos, in terms of these 5 aspects, is the same as Paxos. It's asynchronous, it's for crash fault, pessimistic, the number of nodes are known, and the same complexity matrix as Paxos. However, it says having majority quorums for both leader election and replication are too conservative. So what we need is the leader election quorum and replication quorum must intersect. But there is no need for the replication quorum to intersect with each other. As a result, we can have small replication quorums if there is an intersection between leader election and replication quorum. Basically, we can have a leader election quorum consists of, for example, 6 nodes and a small replication quorum. As long as there is an intersection between leader election and replication quorum, then then we are fine. So it basically, the algorithm is the same as Paxos. It just talking about the number of nodes and the trade-off between leader election quorums and replication quorums. Paxos has many other variants from 1998, where Paxos is presented till a couple of months ago, where Bpaxos has been presented. There are many different variants of Paxos has been presented, and these different variants are for different settings or trying to have a basically reduced number of phases or reduced message complexity or something like that. So we have all these variants. I'm not going to talk about them. And as Amr said at the beginning of the presentation, Paxos has been used in many real systems. It's just that I just list a few of them. So there are many more real systems that are using Paxos Google Spanner is already been presented by ARM. So we have basically in Google Spanner, we have sharding and we have replication. For sharding at application level, we use 2PC and two-phase commit and two-phase locking. And in the basically storage layer, we use Paxos for the purpose of replication among different data centers. Similarly, we have Paxos in Google Bigtable. And in Google Bigtable, we have Chubby, where we have we want to kind of have consistent metadata. And for basically, Chubby is going to be a distributed log service for us. And it consists of 5 replicas and use basically Paxos to keep these 5 replicas consistent. So there are many other systems that are using Paxos. So by that, I'm going to move to another domain.
You gave your tutorial?
I just gave the first third.
Oh. You got part, maybe you have to do another part?
Then I have to do
So far we have talked about crash failures and different protocols in that domain. But what if nodes behave maliciously? So I'm going to talk about the first paper in that domain of consensus, the Lamport paper, because interestingly talking about Byzantine failures, not hash failures. So in this paper, we have a synchronous system. That means there is a bound on the delay. We are talking about Byzantine failures. It is a deterministic approach, and it needs 3F+1 nodes. And it shows that for reaching agreement in the presence of fault, in the presence of Byzantine failures, we need at least 3F+1 nodes. The number of phases is a function of number of failures, which is F+1, and the complexity is O(n)² squared. So in that paper, we assume that okay, we have faulty processes, and to achieve agreement, we need to have 2F+1 correct nodes, which makes the total of nodes as 3F+1. And the idea is we have a set of processes, and each process I is going to construct a vector of length n. N is the number of processes. So each process is going to construct a vector of length n. And if a process is non-faulty, the V of I is I. If process number 2, V of the second element is 2, otherwise it's undefined. So how to construct this vector? Let's assume there is 4 nodes and F is 1. So we have nodes 1, 2, 3, 4. And let's assume the 3 is the faulty process. So node 1 sends its value, which is its ID, basically 1 to others, similar for the 2. But since 3 is a faulty process, it's a Byzantine process, it's not going to send the correct value. It sends different value, let's say X, Y, Z to other processes. And 4 is correct 1, so it sends 4 to all of them. Now each process collects all the values and create a vector. So process 1 receives 1 from itself, 2 from process 2, X from process 3, and 4 from process 2. So each process is going to create this vector. And then it's going to basically multicast its vector to all other nodes. So as a result, each of these correct process got 3 different vectors from 3 different nodes. For example, 1 got it from 2, got it from 3, and got it from 4. And now each process is going to check each of these elements: first element, second element, third element, and fourth element. And if there is a majority in that element, then that's the result. So we have 1, A, 1. So 1 is the majority. So we put 1 here, we put 2 here, but for 3, there is no majority, so it's unknown. And for 4, there is majority. So in that way, we can construct a vector, and we can say, okay, there is a consensus on 1, 2, and 4, and we have a known value for the 3. In the paper, they have a proof that shows that 3F+1 is optimal. We can also have an example with 3 nodes and easily show that, okay, if we have 3 nodes, then these 3 nodes got different vectors. And once we have, for example, once we have 1 and 2 as correct node, there is no majority between elements that they receive. So we cannot have agreement with 3 nodes, basically with less than 3f plus 1 nodes. With that, I'm going to talk about one of the most known Byzantine, basically fault-tolerant protocols, which is PBFT, which is designed by Kostra and Barbara Liskov in 1999. It is an asynchronous process, asynchronous protocol, and it has 3f plus 1 nodes. The number of phases is constant. It's 3 phases, and the message complexity is ON squared. Let's see how it works. So
Mohammed, if I may interrupt. So this is important because we are switching now from a crash model, which the previous protocols kind of were developing, and now he's going to use Byzantine. And so the slides emphasize this. This is very important. It's a change in the way you're thinking. So you have to think of the failures as being malicious. They could lie, they could do all kinds of things. Okay, sorry.
Thank you. Thank you, Am. So yes, as Am said, we are switching, and we can ask this question: why Paxos? Why we cannot have Paxos with Byzantine node? So the first problem is the leader. You remember the leader assigns sequence number to the request, and have to basically have total order between. But if the leader is a malicious node, we cannot rely on the leader. We cannot trust the leader. And the leader, the malicious primary, malicious leader can assign the same sequence number to different requests, or assign different sequence number to the same request. Similarly, we cannot use Paxos for leader election, because we said in Paxos, the intersection of any 2 quorums needs to be 1. But is that one node, is it an honest node, or it might be malicious? Since here we have F malicious nodes, we cannot say the intersection of any 2 quorums needs to be 1. The intersection basically needs to be F plus 1, because we might have F malicious nodes. So for these 2 reasons, we cannot use Paxos in the presence of malicious nodes. So in PBFT, we use 3f plus 1 nodes. It's basically 3-phase protocol, and it uses bigger quorums instead of the network is basically 3f plus 1 nodes, and the quorum size is 2f plus 1. So let's see why we need basically 3f plus 1 nodes. So first of all, to make progress, we need to be able to tolerate F failures. So the system should be able to progress if we have only n minus F processes. However, what if the F that didn't respond, so this F, what if these nodes are not faulty nodes, just slow because of its asynchronous system, their response could receive later on. And F of these n minus F nodes, F from this set of nodes might be faulty. So we need to have enough responses to outnumber these faulty nodes. So basically n minus 2f, where f is the f node didn't answer or answer later, and these f faulty nodes should be greater than f. So as a result, n is greater than 3f, and basically we have 3f plus 1 nodes as the network size. We can have another argument. We said that any 2 quorums of responses need to intersect in at least f plus 1 nodes. Why? Because f of them might faulty, and we need at least 1 correct node in the intersection. So any 2 quorums needs to be at least basically n plus f, because the intersection needs to be f plus 1. So, and a quorum could be like at least f less than a network size. So we have n minus f as a quorum 1, n minus f as a quorum 2, and we want these to be greater than n plus f. As a result, n is greater than 3f. So we have basically quorums of 2f plus 1 replicas, and we have 3f plus 1 replicas in total, and the intersection is f plus 1. So the PBFT algorithm the PBFT protocol has three main components. One is the normal case operation. One is the view changes where we have a faulty leader and we need to switch the leader. And one is the garbage collection for basically saving the storage. So to explain PBFT, I'm going to kind of start with multi-Paxos and then see why we need one more phase of communications and why we need more number of nodes. So in multi-Paxos, you remember multi-Paxos was same as Paxos, but we assume the leader is elected. So we have a stable leader, so the leader is elected, and then we can rely on that elected leader to process many requests. So we assume that, okay, replica 0 is already elected as the leader. So the client sends its request to the leader sends accept message to all replicas, and let's assume the replica 2 is crashed. So it receives one message from replica 1, and in the accepted message, in the Paxos, we said we need f+1 messages, including the primary. So here f is equal to 1, so we need 2 accepted messages. One is from replica 1, and one is the primary itself, so we have 2, and then we send commit messages. What if we assume that the primary is still honest? The primary is not behave maliciously, but the backups might behave maliciously. So in that sense, we cannot say, okay, we need f+1, because f of them might be malicious. So here, we need basically 2f+1 node to make sure that the malicious behavior, the 2f+1 as the quorum size, to make sure that even if the backups behave maliciously, we can still progress. So here the primary waits for 2f+, including itself, becomes 2f+1. Accepted message and then send commit message. So as a result, if we have a trusted primary, if we have an honest primary and malicious backups, we can still have centralized approach. We can still have 2 phases of communication, but we need more number of nodes. An optimization in Paxos is to reduce basically accepted and commit and make them a single phase of communication. So instead of sending accepted message to the primary, and then we have the primary collect all accepted message and see the majority and send, okay, this is committed, we can say, okay, replica can talk to each other. They can send commit messages to each other. And then if I receive 2f+1 matching commit message, I can say, okay, it is committed. There is no need to wait for the leader and then the leader send back the message. So we can kind of reduce one phase of communication between basically accept and commit messages. And then they can send reply to the basically the prime. So now let's go to the PBFT. What if in Paxos we said once the replica receives an accept message, it knows that every replica receives the same message. That means it knows that the primary is trusted. What if the primary is untrusted? So here, once they receive this accept message, because the assumption is this primary is trusted, there is no need to validate this message. We all know that the primary is trusted and it sends the same message to everyone. But what if the primary is untrusted? Then we need one more phase of communication. We need to check with each other. Is the primary sends the same thing to all of us, or it is different? So as a result, once we have the leader is malicious, it can assign different sequence number to the same request or assign the same sequence number to different requests. It can behave maliciously. So we need one more phase of communication to check the primary, basically to check the primary. So it is PBFT. So in PBFT, we have request going to the primary. Primary sends pre-prepared message to every replicas and saying, okay, this is the value. But now replicas want to check to validate this message. They talk to each other and sending message to each other. Did you receive the same thing from the primary or not? If 2f+1 of them say, okay, I have received the same thing, then that means the primary is honest. We can't trust the primary. So we continue. We go to the commit message. And again, we talk to each other. The nodes talk to each other and commit the message. Finally, they send reply to the client. The client waits for F+1 replies. If it receives F+1 replies, it makes sure that, okay, there is some honest node there that execute this message. So in PBFT, we have 3 F+1 nodes. The quorum size is 2 F+1, and intersection of any 2 quorums is F+1. What if we have what if we have a malicious primary? So basically, once a node receives a message from the primary, it basically it starts a timer, and the timer is for some delta time. And the timer, if it receives the answer for that message, if it receives a commit message for that request, then it stops the timer. However, if we have timeouts, the timeouts trigger view change. The timeout means that there was some problem with this coming message from the leader. And the problem is usually the leader is faulty. So once basically the view change provides liveness when primary fails. And if you remember FLP result says that we cannot have safety and liveness in an asynchronous system. So here, that's why we use timeout for liveness. We have safety in an asynchronous system, but we need to have some timeout, some synchrony assumption to provide liveness. And that's why we need timeouts here. So once the timeouts happens, the replica requests the view change. It sends the view change to everyone. If the new primary, the primary of the next view, receives 2 F+1 view change messages, it knows that, okay, everyone is claiming that there is the majority of nodes claiming that there is a primary failure, and we need to change the view. So it sends a new view with that proof, basically those 2 F+1 view change messages, and some instruction on how to deal with the pending messages. I'm not going to go through the detail of that. But the problem is view change has a high complexity, is ONQ, because we have ON square message communication, and we might have consecutive malicious failures. So it is going to be ONQ. And finally, the garbage collection it's trying to discard the message in the log. So we have checkpointing. We periodically checkpoint the state by multicasting checkpoint message. Nodes are going to multicast checkpoint message to each other. And if a node receives 2 F+1 checkpoint message, it knows that it is basically a proof of correctness. It can discard prior message from this, and it is the stable checkpoint from here. And then at some later point, we have another checkpoint. We can discard this part as well. So PBFT is an expensive protocol. As you saw, it needs 3 phases of communication. It needs 3 F+1 nodes. And the message communication is ON square. If you have view change, it could be ONQ. So it is a very expensive protocol. The question is, can an asynchronous protocol, can a Byzantine asynchronous protocol perform better? There are a couple of solutions for that. One is optimistic approaches. Optimistic approaches try to execute transactions without ordering and saying, okay, let's assume nothing bad is going to happen. And if there is some failure, then we need to handle it later on. Or they use active passive replication, saying, okay, let's assume that let's put F of the replicas as passive replicas and then try. I will go through this. There are some protocols that using Zyzzyva is using basically optimistic approach, similarly cheap PBFT using. Another idea is to restrict the malicious behavior of nodes. So you remember we said that the problem is these nodes might send different values. That their leader might send different values to different. We can use trusted hardware to ensure that the leader cannot send different values to different nodes. And this idea used in mean BFT or cheap BFT. Another idea is to explore a spectrum of performance trade-off between different complexity metrics. So we have 3 phases, 3f+1 nodes, and ONS square message communication. We can play with them. We can reduce the number of phases. On the other hand, it will increase the number of nodes. Or we can reduce the message complexity by increasing the number of phases. So we can play with these trade-offs. And these two are used in FAB and HOTSTUFF protocols. So I'm going to go through a couple of these protocols and show that how we can deal with malicious failure in a cheaper way. Zyzzyva is the first one. So just a question, do I need to continue till 2:30, or we could have 5 minutes for questions?
Yeah, I mean, right now, sorry, right now there are no questions that I see. So I think you should stop at 1:30 and we will get back together at 2 o'clock.
Okay, so I think what I'm going to do is I'm going to cover this protocol in the next 5 minutes, and then we'll stop there.
Yes, that sounds like a good
so
idea.
Mohammed, are you sure you'll be able to cover Zyzzyva in 5 minutes?
I think I can.
Yeah, let's try.
Okay, let's try.
Okay, yeah, thanks. So Zyzzyva uses an optimistic approach. So instead of basically having an ordering consensus, it immediately execute the nodes immediately execute the transaction and sending to. So as a result, it can decrease the number of phases to 1. And if there are some failures, then we need to have 2 more phases. And the complexity of messages becomes O of n instead of ONS square. So optimistic approach helps us in that. So what's going to happen? A replica receives a request from the leader, and it speculatively executes the request without any communication with other nodes. So there is no consensus between nodes. They are going to execute first and send the result to the replica, to the client. And it is the client is in charge to check the results. If the results are matching, then we are done. If not, we need to have 1 more phase of communication to ensure that we all agree on the same. So let's see the first case. The client sends a request to the leader. The leader sends a message called order message to all replicas, and replicas are going to execute immediately and send replies back to the client. So you see, there is no consensus here. We receive the message, we execute them, and send them. So if the client receives 3f+1 matching replies, then that is very good because there is no failure in the system. All nodes behave correctly, so we are done. The second case is, again, we have this execution. We send these replies to the client. However, the client receives only 2f+1 matching replies, or let's say less than 3f+1, but more than 2f+1 matching replies. So the client has some timer. It waits for some time to receive more replies. If it doesn't receive more replies, we need to have 1 more phase of communication to tell these 2f+1 replicas that we are going to commit this message. So it sends commit messages to these replicas, and the commit message includes something from these replies. Basically, it includes the signature and some part of the message. And then we have commit and local commit messages to receive 2f+1. And if it receives less than 2f+1 matching replies, then we need to have a view change protocol, which is very costly in case of Zyzzyva. So in Zyzzyva, we have 1 round of message exchange during normal operation, and the view change is more costly than even PBFT because it is optimistic. And if there is need for view change, we need to have 1 more phase of communication. So with that, I'm going to stop for this part of the tutorial, and then we'll continue with HOTSTUFF after the break.
Okay, thank you very much. We still have the second part. I just want to let the audience know that we will assemble back in half an hour at 2 p.m. for another 1.5 hours of the tutorial. So we'll break now. And again, reminder, if you have questions, please put it on QA chat, Slack, so we can answer all those questions as we proceed. Thanks for the audience. Thanks for the two speakers. So we'll continue again. Okay.
Thank you.